In NMR relaxation, let's look at what's actually going on. We actually define two liquid phases. First of all, what is bulk liquid far from the particle surface, and then surface liquid, which is literally bound to the surface of the particle. So when a particle is actually wetted, the liquid basically liquid molecules have to sit and attach themselves to the surface. So the first thing that happens is when that liquid attaches to the surface, it changes both the rotational and translational motion of that bound liquid, and it will be different from the liquid far away from the particle surface. So we describe here a particle, which is orange, and what we have now is in fact the liquid molecules away from the surface in the light blue, and when they absorb on the surface to wet that surface, we show them as dark blue. And so what we now have, we have a relaxation time of the liquid, but we can also have a relaxation time of those particles that are bound to the liquid surface. And the difference between that can be very large, orders of magnitude. And then the changes in the nature and extent of the surface, in other words, the particle size, the particle shape, the particle morphology, and the particle surface chemistry, or even the rate of exchange of the particles of the liquid molecules can be measured probing the using NMR relaxation itself. So let's look at NMR relaxation when we've got a surface, liquid, and suspension. There are essentially three relaxation phenomena occurring at the same time. The first one is, of course, that for the bulk liquid, and then we have one for the surface. Now, the relaxation of the surface basically is exceptionally fast. In a large high field, high resolution NMR, the 300, 400 megahertz, $500,000 instruments, you can actually do solid state NMR. In our case here, this relaxation is so fast that we cannot even see it, so we can ignore it. But what we can measure is that for the suspension and the bulk liquid, and we can see that there's difference, because the relaxation, as I mentioned earlier, for the liquid is much different. It is in fact much slower than that for bound liquid in the suspension itself. Now the relaxation time changes, of course, then with not just the particle liquid, but the amount, the concentration of the particles there, the concentration of the suspension, but also the wetted surface area. So the relaxation of a suspension is dependent upon two factors. One is the wetted surface area, in other words, what's the particle size, and the other one is how much do we have. And we see on the right hand side the relaxation time basically decreases as the concentration increases, and this is an example here for 8 to 10 in particle dioxide. So the important thing to take of this is that you can make a measurement at almost any concentration, but you get the biggest change at high concentrations. So if you're able to work at high concentration, that's good. However, if you want to compare samples, then you have very short relaxation times, you're better off actually having a slightly more dilute system, because you're going to get a bigger change between the two. Now, in the actual measurement itself, we measure a relaxation time, but what we actually use is what's called the relaxation rate, which is simply the inverse of the relaxation time. It's 1 over the relaxation time. And we can see if we take that data for the relaxation time and invert it, we get a relaxation rate which is a linear function of concentration.